Hello and welcome to a new Ostrich video and the start of a new series where I'm going to talk about our flight instruments, how they work and how we use them in flight and what can finally go wrong and how we should deal with the situations. And today we start with the speed indicator. The speed indicator is one of the basic instruments that we have in every aircraft, and it's one of the barometric instruments, which means it uses air pressure to determine our speed. So our airspeed indicator is basically a sealed box that is connected to our static port, and the static port is usually on the side of the fuselage. And as you can see here, it's also additionally protected by this little plate so that no wind is able to blow into this hole, that no water seas can form there and produce an error in the measurement. So we want to really measure only the static pressure resembling the weight of the atmosphere above us. And then inside the box, we also have this little metal can, what is over some linkages connected to our indicator. And our static pressure is pressing from the outside, and the inside of this can is connected to our pitot tube, what measures our stagnation pressure. And the pitot tube is usually installed under the wing or sometimes at the fuselage. But the important point is, as you see here, the opening of the pitot tube is pointed directly into the wind. So when we now want to measure our speed, we measure the difference between the static pressure outside of the can and the stagnation pressure inside of the can. And by measuring this pressure difference, we account for the fact that the atmosphere around us changes its density with the meteorological conditions. And when we're on the ground, the stagnation pressure and the static pressure is the same. So this can doesn't change its shape. And over the linkage, we don't get an indication, or the indication is 0. When we are now in flight, the air is rushing over our fuselage, over our wing, and also into the pitot tube. All this kinetic energy gets converted into additional pressure. So the pressure inside this can is bigger than outside the can, and therefore the can expands, and over this expansion it moves our speed indication. Let's look at the markings on our speed indicator, and the first marking that is important is the unit the indicator is reading in. And in case of our Piper Comanche here, it's miles per hour, because it's an old American plane, on an old German plane, and also in Russian planes you probably will find kilometers an hour, but mostly speed indicators today read in knots. And it's really important to keep this unit in mind because ATC, your weather report, the speeds are given in knots, and if your speed indicator reads something different, you have to keep in mind to make the conversions to keep your speed restrictions. And then we have this color ranges on your speed indicator, what marks your different speed ranges. And the first one is this white arc, what is our flap range. And the beginning of the white arc marks our stall speed with fully extended flaps. And the end of the white arc marks the maximum speed with fully extended flaps. So if you exceed the speed and your flaps are still extended, flaps will probably get damaged. Then we have this green area, what is our normal cruise area. And the start of the green area marks our stall speed without flaps. And then the end of the green area, our maximum cruise speed. Then we have the yellow area, what is for emergency situations, so you can reach up to the speeds to get out of emergency situations, something like this. But you shouldn't stay in the speed range for a long time because this puts a lot of stress on your airframe, and over a long time this will be probably too much for your aircraft to handle. And then finally we have the red marking, and that's the speed you should never exceed because this definitely puts too much load on your aircraft and your aircraft structure will suffer from it. When we use our speed indicator, we have to keep 3 different airspeeds in mind. And the first one is our indicated airspeed, what is basically just the speed we read off our indicator. Then we have the calibrated airspeed, what is our indicated airspeed corrected for the instrument's error. And the instruments are built in this way that the instrument error at normal cruise conditions is so small that we can briefly ignore it and take indicated airspeed and calibrated airspeed equal in these conditions. On the other hand, when we are at slow speeds with extended flaps and high angles of attack, like in takeoff or landing situations, this instrument error can be significant and we have to correct for this. And the reason why it's so different is because our flaps and the angle of attack changes the way the air is flowing over our fuselage and the way the local pressure is created around our aircraft, and that results in big difference in the instrument reading. And to correct this, you have to look at your owner's manual, at your flight handbook, and there you find a table what says with this configuration, when the indicated airspeed is so high, your calibrated airspeed is so high. And last, we have our true airspeed. Our instruments are built with the ICAO norm atmosphere in mind and are calibrated for sea level. So if you're flying under the norm atmosphere at sea level, your indicated and your true airspeed would be the same. But actually, we nearly never do this. The temperatures can be different, the pressures can be different, and we usually don't fly at sea level. So we have to correct for the density differences in the air. And you can assume our rule of thumb says like for every 1,000 feet you gain, your speed indicator will indicate 2% less. So if you, for example, are at 3,000 feet and your indicated airspeed is 100 knots, your true airspeed will be around 106 knots. If you need a more accurate figure and also calculate for the temperature difference, you have to use your flight computer. Or in some cases, you are lucky enough, like in our Piper Aztec, that you have this part of the flight computer built into your speed indicator. So we see here, we have our outside air temperature, and we can set our altitude below the actual temperature by using this little knob here. And this corrects our speeds down here so that we can read off our true airspeed directly at the indicator, what can be really, really handy. And you see, it's only doing this for the upper speed regime because there the change would be much bigger than in the lower speeds. So let's see what can go wrong and how we can deal with the situations. And we start with a blocked pitot tube, maybe due to debris or icing. And when the pitot tube is blocked, we basically can have two outcomes. So if only the front of the pitot tube is blocked and the drain port is still free, the pressure inside the can will escape over the drain port and our speed indicator will go to 0. And in the case the pitot tube and the drain port is blocked, the pressure is trapped inside the can. And from this point onwards, our speed indicator will act like an altimeter. So when we climb, our speed will rise, and when we descend, our speed will fall, no matter what the speed is actually doing. And for example, what can happen, you are in the climb at 120 knots, you're going to cloud, your pitot tube freezes completely, and from this point onwards, your speed will rise as higher you climb. And it will continue to climb even if you do your countermeasures, pulling back the throttle trim for a lower speed. And your indication will say you are going faster and faster and coming closer to overspeed, while in real terms you're coming closer and closer to a stall. And you see this can be a really, really dangerous situation. So to avoid this, always check for debris before and also put on your pitot heat if you are in danger of icing conditions. And that's so important that basically every aircraft has a pitot heat, even our Piper Comanche, what is not really equipped for icing conditions. So, and let's see what can happen when our static port is blocked, for example, due to clear ice forming on our fuselage. And in this case, we usually have a much bigger problem because our altimeter and our vertical speed indicator will be also affected. And it's also a bit harder to detect because Let's say this blockage happens at 3000 feet altitude. If we stay at this altitude, speed indicator will just work fine. But if we climb above this altitude, our speed indicator will indicate a speed that is too low. So we are actually going much faster than our indication. And if we're going below this altitude where the blockage happened, our speed indicator will indicate a speed that is far too high than what we are actually doing. And to solve this problem, of course, you should check for blockage during your walk around. And if it happens inside the air, we are in the lucky position that most GA aircrafts don't have a pressurized cabin. So they have the option to have a secondary static port inside the cabin. And you can switch to this. Or if this secondary port is not available, you also can smash the window of your instrument and let the static pressure inside the instrument via the smashed window. So that was it about our speed indicator. I hope you enjoyed the video, and if you have questions, as always, write them in the comments below and I try to answer them as quickly and correctly as possible. Then all is left to say thanks a lot for watching and see you at the next time. Bye bye.